Okay, so this module finishes up by looking at universal gravitation and planetary motion. And your lab is going to be a lab that's exploring the relationship between mass and distance, between objects of mass and the gravitational force of attraction between them. So let's kind of talk about the background information, and then we'll talk about the lab. So first of all, what Newton realized was that the force that kept the moon in orbit, that provided the centripetal force to keep it moving in a circle around the Earth, was the gravitational force acting on the moon. So that means that just like you, when you stand on the Earth pulls down on you with a gravitational force called your weight. You pull back up on the Earth equal and opposite due to Newton's third law. And we talked about action and reaction pairs. So the action is the Earth pulling down on you, and the reaction is you pulling up on the Earth. And both of those forces are equal, although they may not seem to be, because we definitely, if we step off of ledge, we can see the result of that force, right? Because we have a lot less mass. So the force acting on that mass produces a more acceleration because we have less mass. But the Earth has an immense amount of mass, and so that same force is just not enough to overcome its inertia to see it accelerating towards us. The moon is attracted to the Earth in the same way. It is pulled on with a gravitational force, its weight, and it pulls back equal and opposite on the Earth. But the Earth is more massive than the moon, so you don't really see the Earth's motion around the moon due to that. But the key here is that the pull is equal and opposite. Let's learn a little more about that.
Intelligent diagramming easy and helps your best ideas become real.
Professor Dave here. I want to tell you about Newton's law of universal gravitation.
He knows a lot about the science stuff. Professor Dave explains.
We learned about Newton's laws of motion, but there is one more law of his to discuss, and it's a big one. It's Newton's law of universal gravitation. In possibly one of the greatest strokes of genius in the history of mankind, Newton looked at the motion of the planets in their nearly circular orbits around the sun and understood that the centripetal force causing this motion was precisely the same force that causes objects to fall down towards Earth, which we call the gravitational force. In this way, he proposed that the planets are in a kind of free fall towards the sun, just the same way that the apple that mythically hit him on the head to produce this insight was in free fall towards the Earth. The objects differ greatly in size, but the concept is the same. Newton corroborated this notion with a thought experiment. When a cannon fires a cannonball, the ball eventually hits the ground. If another cannonball is fired with greater force, it will go a little further before hitting the ground. If a cannonball could be fired with an incredibly immense force, it could produce a speed so great that the ball would never hit the ground, since it would fall at the same rate that Earth's curvature is produced. It would thus always be falling towards the Earth, but never hitting it. Such an object would be said to be in orbit around the Earth. Of course, no cannon can do this, but we have finally achieved this feat with all of our satellites and space stations, which are brought up to orbit on rockets. These are very far from Earth's surface, and they are moving with such great speed that they, along with anyone on board, are always falling towards the Earth, but never hitting it, in a free fall, just like Newton's apple. This means they orbit around the Earth indefinitely at a fixed speed and radius. The same can be said for all the planets around the sun. This gravitational force can describe the motion of every object in space, and it is the case that every object that contains mass will exert gravity on every other massive object. Of course, to feel the effects of gravity, we must be near an enormous object, like a planet. But it is completely accurate to say that gravitational force is exerted by your car, your refrigerator, even you yourself. It is just that this force is completely negligible compared to the gravitational force exerted by the Earth. Newton developed an equation to quantify the magnitude of the gravitational force between two objects, and it looks like this. where F is equal to the constant of universal gravitation, g, times the mass of the first object times the mass of the second object divided by the distance between them squared. This constant, like any other constant, simply exists so that a natural phenomenon like gravity can be expressed in our own arbitrary man-made units, and it is equal to 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. These are the units that will cancel out the units on the masses and radius, so as to give a value for force in newtons. This value was not known to Newton at the time, but was determined experimentally about 100 years later by Henry Cavendish. When discussing the radius between two objects, we will take the distance between their centers rather than their surfaces, as Newton showed that the gravitational force exerted by an object depends only on its mass and not on its volume, meaning that when discussing gravity, we can treat everything as a point-like mass. He had to invent the calculus to do so, much to the dismay of math students everywhere.
Good grammar and
All right.
spelling are important, but if you want to write essays that
So, the big point here is that any objects of mass attract each other, okay? And that universal law of gravity says that force of attraction is equal and opposite. So if the Earth pulls on you with 200 newtons, you pull on the Earth with 200 newtons in the opposite direction. Also, it depends directly on the masses. So if you double your mass, then the force would double. If you double the mass of the Earth, then the force would double. If you double both the mass of the Earth and of you, then you will have 4 times as much force of attraction or weight. It is also inversely related to the square of the distance. So remember, an inverse relationship is one where if one value goes up, the other value goes down, or if one value goes down, the other value goes up. This is an inverse square relationship. So if I double the radius, the force will not just be 1/2 as much, it'll be 1/4 as much because you have to square the half. If I triple the radius, the force will be 1/3 squared as much, or 1/9. If I quadruple the radius, then it'll be 1/16 as much. So imagine that you're on the Earth and you weigh 200 pounds. If you go to a space that's twice the radius of the Earth, you've doubled the radius, and your weight will be 1/4 as much. So the inverse of 2 is 1/2, and then you square that, 1/4. If I triple the radius, if I go to a point even further out, like say way out here, at 3 times the radius, then it's an inverse relationship, 1/3, but it's 1/3 squared. So you'd be 1/9 as much. So if you weighed 200 pounds, you would take 200 and divide it by 9. Now, what does this all have to do with satellite motion? Well, it means that the further you are away from the Earth, then the less force you have pulling on you. And in the case of the moon or a satellite, the less force of attraction, the less centripetal force. So you're not going to travel as fast. So Johannes Kepler was the one that kind of came up with the laws that actually more accurately described the motion of the planets, because previously we had tried to fit the motion of the planets in a scheme where the Earth was at the center of things. And after Galileo kind of postulated, hey, I've got some evidence that might not be true, another guy named Tycho Brahe did a bunch of observations trying to prove that Galileo was wrong. And Kepler was his understudy. He was doing like an internship with him. And when Tycho died, Kepler created a new kind of geometry that wasn't based on circles. He realized that the data that tracked the planets and predicted where the planets would be at different times of the year in the sky could be could fit a model where the planets traveled in ellipses around the sun instead of circles around the Earth. And the orbits were elliptical, and the sun was at one of the two foci of the ellipse. The other thing that Kepler said was that planets sweep out equal areas and equal times. Well, what does that mean?
Consider our planet Earth in space and these sample positions of an Earth satellite in circular orbit. Before the idea of inertia was understood, people thought that a force in the direction of motion was responsible for motion. They imagined angels pushing on the planets. Newton changed all that and taught us that the only force acting on a satellite acts toward the body it orbits. That's the gravitational force. And what if this force disappeared? Then the satellite would fly off in a straight line path. No force, no orbital path. Note that each of the force vectors are the same size and point to Earth's center. Same size because the satellite circles at the same distance from Earth. Note also that they're perpendicular to the orbital path. The 90-degree angle means there's no component of force along the orbital path, which further means no change in speed. From an energy standpoint, that means no change in kinetic energy. And since distance remains constant, no change in potential energy. So both kinetic energy and potential energy are constant all along the orbital path. So a satellite in circular orbit effectively coasts at an unchanging speed all the way around and around and around. Now things are different for a satellite in an elliptical orbit. Consider these sample positions for such a satellite. Since the distances from Earth are different, the forces are different. Weaker far from Earth and stronger when closer, in accord with the inverse square law. So the speeds are different also. Kepler was the first to discover the elliptical paths of planets about the Sun early in the 17th century. He discovered that planets travel fastest closest to the Sun and slowest farther away. But he had no explanation as to why. Just as a projectile tossed upward slows as it rises and speeds up as it returns, so it is with any satellite. Kepler never viewed a satellite as a projectile. That planets are projectiles falling around the Sun, just as our moon is a projectile falling around Earth. This way of thinking escaped Kepler. Let's talk energy conservation. The sum of the potential energy and kinetic energy at any point along the satellite
Let me
path
stop
is the
right
same
here
as at any...
and talk about this equal areas and equal times. So basically what that means is that when the planet is closer to the sun, it travels faster. So it's going to sweep out, say,
The other point.
it's going to sweep
Yeah,
out
with
a
the
larger area in a short amount of time. When it's far away, the gravitational force is less, and so it will sweep out less distance, but in a slower time. Actually, let me just repeat that. I said it'll sweep out less distance in an equal amount of time because it's traveling slower. So imagine it's traveling 100 kilometers per hour
Kinetic energy is
close.
greatest. Potential energy.
100 kilometers per hour close to the sun. So in an hour it travels 100 kilometers. But if it was only traveling 50 kilometers when it's far away, it would only go 50 kilometers in an hour. So that pi wedge that it would travel through would be longer and shorter. And when it was closer, the pi wedge would be fatter and shorter. But if you were to calculate the area of those pi wedges, they would be the same. Kepler described it in that kind of weird way, talking about equal areas in equal times, because he didn't understand and was not aware of universal gravitation. So enter Newton. Now we have a physical explanation of why that happens. It's true what Kepler observed. He could mathematically prove it, but Newton was able to say, well, that's because the gravitational force is less when the planet's further away at the other side of the ellipse. So it travels slower because it has less force on it. And when it's closer, it has more force, so it travels more quickly. And then finally, the last thing he said the ratio of the period squared to the orbital distance cubed is constant. And what that allowed him to do was to accurately predict the period as the time for the planet to go around the sun. So if he knew the period, the time for, say, Mars to go around the sun, and he could estimate the distance to Mars, between the sun and Mars, he could use that, and he could measure the period for, say, Saturn, and then he could use that information, because if he took the period squared of Mars and divided it by the distance cubed, that ratio would be the same for the period squared of Saturn to the distance from the sun for Saturn cubed. So it became a mathematical problem, but he was able to create a map that actually was able to predict periods and orbital distances of planets in the sky, so that he could use that as another tool to predict where they would be at different times of the year, and it worked well. So Kepler, once again, is the guy that kind of came up with those three laws, but just remember, he wasn't aware of Newton's ideas yet. It was kind of, they were kind of going on at the same time, but they weren't really communicating. So after the fact, after both ideas were presented, then scientists could see that there was a relationship. So sometimes it's kind of nice when you have one scientist thinking about a problem in one way and coming up with a model for it, like Newton did with universal gravitation, and then you have another one thinking about it in a totally different way with geometry, not thinking about forces, because, remember, Newton had to create calculus to be able to prove his model. Kepler was using a kind of new math. He was looking at a different shape other than a circle. He was looking at ellipses. And so he was able to use this new geometry and use that with data that Tycho Brahe had collected, observing the motions of the planets. He was able to say, hey, this doesn't support an Earth-centric or a geocentric universe. It supports a solar-centric universe. And the end result is they both came up with the same predictions, that when planets were closer to the sun, they would travel faster, and when they were further away from the sun, they would travel with less speed. So it's important to kind of note that this is a great example of how two scientists can be thinking about a problem in two very different ways, but come up with the same results that actually support each other. So that adds validity to the whole theory. All right, so your lab is going to have you go to a applet. And the applet is a PhET applet this time. It's not at Physics Classroom. It's a PhET simulation. So you can do a lot of things. You can change the mass of both masses, and you can measure the distance. So for example, if I have 100 kilograms, and then I take this and I place the 0 at the center of the blue, and then I measure how far out it is to the next center of the red, it's 4 meters. So that would be the distance, 4 meters. And when a 100 kilogram mass and a 400 kilogram mass are 4 meters apart, the force on each is 0.0000000166,852 newtons. So if I were to bring this closer and cut, let's say I double the distance to 8, it should be 1/4 as much. So if you take that original number and you divide it by 4, you should be getting 0.0000041713 newtons. And in the data chart, you're going to be experimenting with doing different things like changing the masses or changing the radii. You might set both of them to the same mass and then increase the distances. You might double a mass. I mean, the lab tells you what to do. But in the first one, you're just going to be looking at the effective distance on gravity. You should expect that when you fill out your data table here for the first, the effective distance, you're going to expect that they both experience the same force. So both of these columns will have the same answer given to you by the applet. And then you're going to start changing the mass. You're going to keep, for the first couple, you're going to look at what happens when you change the mass of one mass. For example, you'll go from 50 to 100 kilograms, and you'll see how that should double it. So you should see whatever the force is to start with on both of these, they should be the same. When you double that mass without changing the distance of just one, it should double. And if you double the mass of both of them, it should double once and double again. So these would be 4 times. And so you're going to be looking at that direct relationship between mass and gravitational force and the inverse square relationship between distance and force. And then you'll answer a few questions about it. So make sure that you answer your questions in complete sentences. I would go to this, open this up and go File, and I would either make a copy of it onto your Google Drive, or you can download it as a Word document and then type your answers in and save them. And I am going to put a link in here for you to submit your assignment. So let me just do that right now. I'm going to put an assignment link in here. Lab 9 assignment link. And you are going to attach your completed lab to this link by midnight on 3/25. Because that's the day of our lab, and that's when labs are due. And make sure you are logged into your Google Cougar mail account in order to access the Lab 9 Google Doc. So you're just going to submit that here this day. I'm going to put the due date in here for you as, actually I said the 25th, but I'm sorry, I meant the 21st. That's when we meet again. Well, we're supposed to be meeting. We'll put it at midnight. And you can make 100 on it. There we go. So let me just change the due date on that real quick. Make sure you understand that that would be Monday, the 21st. There we go. So you have Lab 9, and you have this video, and so we're going to post a link to this video so that you can watch it. And if you have any questions, please email me. Thanks.